So our title is Tapering Solids and Spheres, and there's really two equations we need to know for this. I guess our first question is, what is a tapering solid? Last lesson we spoke about regular solids, or prisms, and how they pass what I call the toast test, as in we could cut it into slices, and each slice would be identical sizes. Tapering solids are things that end at a point, like these two. And no matter how we slice them, each slice is going to be a different size to the last. And they can go from points from a circle up to a point, square up to a point, or triangle up to a point. In fact, they can go from almost any shape and taper to a point. Now, for tapering solids, the volume formula is simply, volume is area of the base. So if the base is a triangle, square, circle, you need to work out the area of the base, times height, times a third. And sorry, I forgot to write that in type. So it's a third area of base times height. Now, spheres are different, clearly. They have no point. Everyone knows what a sphere looks like. It's a soccer ball, netball, etc. The area for a sphere is 4 on 3 times pi, and I'm sorry I couldn't find the symbol for pi, times r cubed. So we're used to seeing things like pi r squared, but with volume, it's r cubed. And you can remember that because the units are going to come out as centimetres cubed or metres cubed, and so will the volume. Alright, let's do an example. So, give it your best shot, yes. I didn't draw it, I cut it straight off the internet.
Of course you did.
Clearly.
You just drew it. I'm not going to.
Draw a triangle, put a point above it, then connect all the lines from the vertices of the triangle up to that point. I'm making it sound a lot easier than it is, yes, I know.
Yeah, you didn't draw it.
Yeah, well, you know, I'm new age, up with technology. You guys are still with pens and paper.
It's not our fault.
This is true. Although I hear the school's talking about getting the students to buy tablets instead.
Yeah, but they would not us get it.
No, you do.
Because Carla and I went to see if we get the silver mat.
We're not allowed to.
What if I pay more? It's just not possible.
It's just not possible. We just can't.
Can't we pay extra? It's not possible.
Why is
It's
it
got like
possible?
1,000 down there. I don't know. I'm going to buy, you know, those Microsoft Surface tablets for the connected people.
That's what I'm holding, yeah.
Is that, oh, yeah, I'm going to get one of those next year. Are they easy? They cool?
Pretty cool.
Hey,
I enjoy it. It's not really good.
Mine, I don't even know what that's meant to be. It's like a diamond.
Alright, so all of you have some attempt at a triangular based pyramid. Don't shush, Miss Crystal. Alright, so what the formula, yeah, I haven't put measurements on there yet, but the formula we're using, volume is equal to area of the base times the height. Now, what shape's the base? Triangle. How do we find area of a triangle?
Half the base times height.
Yes.
You've got the times a third.
I always do that. Thank you. Yes, times a third. Times height times a third. Now, our problem is we have two different heights. We use h for both the height of the triangle at the base and the height of the tapering pyramid. So we need to be very careful in the equation that we need to differentiate between the two of them. So let's, well, for example, look at here. That height is the height of the triangle down the bottom, and then we have height is the height of the pyramid. Yeah. Now, it sucks first time you see it, but once you understand that all you're trying to do is find the area of the base, that first, and then just multiply it by a third and the height of the whole thing. It works out systematically for all tapering solids. So let's give us some measurements. Let's imagine that the base is 10, the height of the base is 7, and the height of the whole thing is 12, and they're all centimetres. So substituting in numbers, we have a half times the base, which is 10, times the height of the triangular base, which is 7, and then over here we have times the height of the whole thing times a third. So many numbers, yes? 100 and what? Yeah. It worked out exactly. And what are our units? Yeah, centimetres cubed. Alright. Second example. Beautifully drawn. It's not too bad. Just draw a circle and extend it up to a point. If you can't draw a circle, find a glue stick or something in your pencil case and trace around it.
It's like an oval.
Yeah, okay.
That's not real. So you can put that on blue. Mine looks like a pop hat. Why do you make it pretty as well?
Alright, you will get a cheat sheet, but it's worth memorising this formula. So which formula are we using?
403 times 5 times 12.
Yeah, you'd be right if we had a sphere, but that's not a sphere. That's a tapering solid.
Base times height times the
Yeah, volume equals area of the base times the height times a third. And since our base is circular, we find the area of the circle by doing pi r squared, and then we say times height times a third. Okay. And only at this step do we need to look at the numbers. So the radius is 6 meters, and the height can be 14 meters. Substituting in the numbers, we have pi times 6 squared times height, which is 14, times a third. And for most measurement questions, we go to 2 decimal places. Final example. Now you can yell it out, Nikki. It's a sphere. Yep, just draw a circle. No, don't worry. 4 on 3 pi r cubed. Now, clearly, if we had half or a quarter of a sphere, we can multiply the entire volume equation by a half or a quarter to find half or a quarter of the entire volume. But here we just have the whole sphere. Let's have a radius of 2 millimeters. It can be a little ball bearing thing.
I got 33.5.
One sec.
What did you get?
33.51. Nice one. And now, to practice some of these, so all of them are tapering solids. You go to page 132 and do questions 2 to 6. And I'll come around helping you as I need. Yes, there are lots of them. If they've given you a picture, you don't have to redraw it. Alright?
We're going to have to do a question 3. 4 and 5.
Yeah, so if they give you a picture, you don't have to redraw it. If they haven't given you one, you need to draw it to work off it. Yeah, we will do some conversion questions to start off. They're quick. So capacity is the amount of liquid a container can hold, and we measure it in litres. So it's very much related to volume, and because it's related to volume, we need to be able to go between units for volume and units for capacity. And the most important one, by far, is this one here. We need, if you remember that 1 centimetre cubed is equal to 1 milliliter, then you can work out most of the rest. Another useful one to remember is that 1 metre cubed is 1,000 litres. If it helps you put into a little perspective, imagine your 1 litre milk carton. I know not many people buy the 1 litre milk cartons anymore, but 1 litre milk carton, that is 1,000 cubic centimetres. And if you were going to stack up 1,000 of those 1 litre milk cartons, they would form a volume of approximately 1 cubic metre, which is like you spreading your arms out a little, that wide by that high, and that's 1,000 milk bottles. Alright? Now, we've already gone through unit conversions on how to get from centimetres cubed to metres cubed. Does anyone remember how to go from centimetres cubed to metres cubed?
Times by 100,000.
Good. It would be divided by 100.
Square. It's 100 cube actually.
Oh, it's close.
Why do we square it?
Why are we cubing it?
Because it's in like
Yes. So we go from centimetres to metres by dividing by 100. We go from centimetres cubed to metres cubed by dividing by 100 cubed. Have a look on the right hand side. How many millilitres in a litre? 1,000 litres. It is. Yeah, 1,000 millilitres in a litre. So how do we go from millilitres to litres? Yeah. And from litres to kilolitres, again, there are 1,000 litres in a kilolitre, so we divide by 1,000. And going the other way, we multiply. and we multiply. Has everybody got that?
Is that meant to be times by 100 on the last one between the liters and meters?
Yes. 1,000. Alright, I'd like to highlight the slight difference between capacity and volume. Most of the questions, when they ask for the capacity, you just think about how much can fit inside it. However, occasionally questions ask for volume and capacity, and these questions is a difference. Yeah, so what it is a big cylinder outside of a little cylinder, and in between the two. Yeah, you've done the question with cylinders before, but not with volume and capacity. Right? So you can think of this as a thick drain pipe, if you like, a huge drain pipe. And the radius of the larger circle is 3 meters, and the radius of the smaller inside circle is 2 meters. Sorry, my diagram is not hugely clear. And the length of each of these drain pipes is 8 meters in length. And we would like to work out the capacity and the volume. The outer circle, the bigger circle, has a radius of 3, and the inner circle has a radius of 2. Now let's leave capacity for a second and do volume first. What sort of shape do we have? Is it tapering or is it regular? And Kiralee, how do we know it's regular? What defines something as regular? What can we do to it? Huh? Yeah, because we can cut it. So every slice will be the same. So if we sliced that horizontally, putting slices across it like this, each slice could be the same and would look like rings, and each one would be identical. So it passes our toast test. Each cross section is the same. And now what we need to do is find the area of one cross section and multiply it by the height. So what we have is 2 circles, a big one, that's not a circle, a big one and a small one. With radius 2 and radius 3, both meters. And to find our volume, we want area of base times height. And it's not times the third because it's not tapering. It's just the area of the base times the height. And the little diagram I've drawn gives us the base. Imagine looking at the cylinder from above. Which one?
The one you did in the bottom section.
Yeah, it'd be part of the working. So when working out volume, it's quite helpful if you can't see the cross-section easily to draw an example of the cross-section, especially if it's made up of 2 or more shapes. So we really only want the area of what I'm shading in green. And we find that by doing the area of the big circle, take the area of the small circle. Yeah. So remember when we were going through our area equations, we would label them 1 and 2, and lots of you did that nicely in the folio so I could follow it. how would we find the area of 1?
Pi times 3 squared.
Times what? Times 3 squared, yeah. Equals 9 pi. And you can put that in your calculator and come at it with a number if you'd like. And if we want to find the area of 2, same formula again because it's a circle. Pi r squared, except this time it would be pi times 2 squared, which equals 4 pi. Do stop me if I'm going too fast.
Why don't you just show me work out the formula times and divide?
You could, yeah. So you could work out the volume of the big cylinder and the volume of the small cylinder, and then do big take small.
That's what I was thinking.
Maybe here, but for most problems, you'd want to find the volume by doing area of the cross section times the height, rather than working out 2 entire volumes first. You'd get the same answer, but you're right. There are different ways of doing it.
Would we lose marks because of it?
No. As long as you showed your working and did logical steps and got the right answer, you'd be fine. Alright, so our area of base is equal to 1 minus 2, or 9 pi minus 4 pi, which equals 5 pi. If you put that in your calculator earlier and got numbers, that would be fine. So area of the base is 15 point something. 15.71 meters squared. And now we look back up to our formula for finding volume. We wanted the area of the base multiplied by the height. We found the area of the base. The area of the base is 15.71, and now we need to multiply it by the height of the cylinder. So our volume, oh god, is equal to the 15.71 multiplied by the height. Meters cubed. Is that what you got?
I got 22.
Did you put 15.71 into the calculator, or did you put the 5 pi into the calculator?
17.7.
Okay, so that would technically be called rounding error, because you know how we rounded it at this step here? We rounded 5 pi to 15.71.
Normally what I do is, if I work out that, and then I'll just go like...
You keep it on the calculator screen and do the... Yeah, so if you keep it on the screen, you don't get the rounding error, and you get that.
If you put 5 times 8,
Yeah. So that the difference between the two is the rounding error. But as long as you're clear of the test, it wouldn't make a difference. Alright, so that is the volume of this cylinder. What about capacity? And capacity is how much water or liquid we can fit inside it. Alright.
that's in meters.
Yeah, you're on the right track. So if we find the volume of the interior cylinder in meters cubed, we can then convert it to litres or to kilolitres. Note that 1,000 litres is also known as a kilolitre. Alright, so for our capacity, we simply want the volume of that inner tube, which is a circle with radius 2 times the height. So volume equals area of base times height. Area of base is easy, it's just pi r squared, pi times 2 squared. Therefore our volume is equal to 4 pi times 8. So once we found the volume of the cylinder, we need to convert our units into a unit of capacity, going from meters cubed, spread out there, into either kiloliters or liters. .53 kiloliters. But I guess the important thing to note is the distinction between the two. So the capacity of it is 100 kiloliters, whereas the volume of it is 125 meters cubed. Are you happy with the idea of the difference between the two? Because one is the amount of space it takes up, the other is the amount it can hold. And the reason it's different is because it's got quite a thick wall. Alrighty, so for the rest of you, go on with the original volume questions. For those of you who have finished the volume questions, you can go to page 135. Questions 1 and 2 are conversion questions. Do them, they're good practice. 4, and then it's all good practice. We'll do 5 to 11. You won't do that today, but we can.
We're doing 1, 2, and 4 today.
Well, 1, 2, 4, and we'll finish 5 to 11 tomorrow, because homework will be your folios. Smile.